Hello everyone, welcome to another session of Reinforcement Learning Reading Club. Today we have Aidan Scannell, postdoc researcher at Aalto Robot Learning Lab, and he's going to present a very recent paper published on arXiv about model-based reinforcement learning. So Aidan, you can begin.
Okay, thank you, Armin. I'm going to present a simplified model-based RL, learning representations, latent space models, and policies with one objective. So I actually found this paper when I was looking through the NeurIPS proceedings, and it's not actually there. But some of the authors have another paper, which I think they called Joint Model Policy Optimization of a Lower Bound for Model-Based RL. And I thought sounds like quite an interesting idea. And then there was like another paper they've done along a sort of similar line. And yeah, I think it's just an interesting direction for work. So yeah, please interrupt me during the presentation if anything's not clear, or if there's anything you want to discuss. You can either like raise your hand or just like unmute yourself and shout out. Okay. So some preliminaries. So in RL, we want to find some policy which maps from a state S to an action A. And the idea is that we want to maximize the expected sum of some discounted rewards. So here, R is our reward function, and it tells us like how happy we are performing a given action in a certain state. And the idea is we'd like to maximize these for all time steps. And in order to get some theoretical guarantees, we add a discount factor gamma. And in this work, they also put 1 minus gamma in front of the sum. And we can kind of ignore this for all intents and purposes, like we're just timesing by a constant, but it helps with some of the derivations in their work. So the interesting part then is that the expectation, so here the transition dynamics P, this comes from the real environment that the agent is interacting with. And because we don't know this, all we can really do is interact with our environment to get samples in order to evaluate this expectation. So in model-based RL, the idea is, can we learn a representation of the environment? So here we now have P theta, and this is a representation of the environment. And can we then use that to do reinforcement learning? And the idea is we'd like to improve our sample efficiency. So we'd like to interact with the environment less in order to learn the same amount. And model-based RL is like, it's a bit more complicated than this, but this is like the general idea. We now want to learn a model of the environment and then use that for RL. And commonly, we have like what's on the left plot here. So you learn your dynamics model and you have some loss function, for example, the mean squared error. You then try to optimize your policy using a policy loss, often the one on like the previous page, but like approximations to it. And then some representation. So this is if we have high dimensional inputs like images, we might want to map these to latent states. And this is kind of like the standard setup for model-based RL. The main goal of this paper is to say, okay, instead of having these 3 different objectives, we want to combine them all into one objective. And they do this by making a lower bound on the reinforcement learning loss. And they call their methods aligned latent models. And I think the idea is that the alignment comes because the different parts, like model policy and representation, are aligned with the lower bound. Okay, so the figure on the left kind of shows their setup. So you have these high dimensional states or observations. So here they're images. And we have an encoder. And the encoder maps from this high dimensional state space down to the latent state Z. So here the encoder is E phi. Then once we're in the latent space, we have the dynamics acting on the latent state in an action. So here the latent dynamics are M phi. And they then propose to a latent space policy. So here the policy maps from a latent state to an action. So this means you can take a single observation, map it to the latent state, and you can completely unroll the policy in the latent space without any access to the images. Yes, Armin.
Oh, sorry, I thought I can't see your mouse pointer, but now I can see it. Yeah, okay, that's
okay. Yeah.
Sorry.
That's okay. Yeah, so this is kind of like the general setup, and it kind of contrasts like some work. So some work, like from the latent states, they'll have a decoder where they'll try and regenerate the image. And then they have this reconstruction loss between the image generated by the decoder after going through the latent dynamics to reproduce the observation. Whereas this work is different, like you only have the encoder. So you have this, what's called a latent state consistency term. The idea is you want the latent state through the dynamics to match the prediction from the encoder taking the image to the latent space. And this has been done before. This was done at the TD MPC paper. And I think it's very similar to what Yi's been working on. Okay, so they don't really talk about this in the paper, but I personally think it's quite important because they essentially formulate this lower bound through probabilistic inference. And in order to do this, you introduce this optimality variable, which is a Bernoulli variable, and it takes a value of 1 if it's optimal and 0 if it's not optimal. And the reason that you do this is you can formulate a likelihood where you say what's the probability of being optimal given my trajectory tau. So here the trajectory tau is not just the states and actions at all time steps, but also the latent state Z. And that's quite important and something that I haven't really seen before in prior work. And the idea is that this likelihood will be proportional to the sum of the rewards. And they say this because the reward function is always positive. But yeah, I mean, they don't really ever introduce it this way, but I think this is a much nicer way to think about it. And then the prior over trajectories then. So you have some initial state distribution where you get a state. And then the idea is the distribution over the states come from the environment's transition dynamics. So here at each state, you map it to the latent state using the encoder in order to use the policy, because the policy is in the works on the latent state. And so the way to really think about this is, if we'd go back to the previous slide, we're essentially unrolling the dynamics in this high dimensional space, but we're kind of getting to the actions by coming down to the latent space and back out. And the reason that this isn't very good is that to draw samples from this distribution, you need to interact with the environment. And what we really want to do, or a way around this, would be to approximate the expected discounted sum of rewards, which is essentially the marginal likelihood when you think of it about using this optimality variable, with samples from another distribution Q. So anyone that's worked with variational inference, lots of bells will be ringing here. And essentially we can just lower bound the expected return using this other distribution. And we get here by using Jensen's inequality, by moving the expectation outside of the log. But this isn't super important for now. But the basic idea is we want to come up with some distribution Q, which is easy to sample from. so we can calculate this lower bound. Okay, so this is the variational distribution they propose. So it's quite long, but it is fairly simple. So I'll talk through the different terms. So you have your initial state distribution. So you draw your state. Then we use our encoder to map to the latent space. And the important thing here is this only happens once. So we have this first high dimensional input and we come into the latent space. And we never really go back to the high dimensional space. So now we can simulate the dynamics now fully in our latent space. So that's what happens over here for our latent space dynamics, policy, which are all acting in the latent space. So now we need to get the joint distribution over the states as well. So we put this environment dynamics in here as well. But the key point is that after t equals 0, the trajectory over the latent states is independent of the trajectory over the actual high dimensional states. And that's really important because it means you can estimate this bound using samples from the latent space model. So that means you can use any policy and unroll it in the latent space and use it to get estimates of the bound. And this means that you don't need access to the high dimensional states. And so the reason they introduced this K to say you're using like a K step rollout. I do find the notation of doing this like sum to infinity quite weird because they may as well have just not introduced a K. But anyway, like it doesn't really matter. Okay, and so this is the objective that you get. So all they've done here is we're substituting our variational distribution back into the bound that we got with Jensen's inequality before. And we have a sum of some discounted reward. So this is like an augmented reward function. And the idea is that this is after our horizon K, we can use our action value function to bootstrap this. And if we now look at the reward function, we have this extrinsic term, which is like the reward, which comes from the environment. So this is what you would normally see, albeit with this extra term in front. And then we have the intrinsic term. And so, you know, this is looking at the encoder, the distribution over the next state from the encoder versus the distribution from the latent space dynamics. So this is kind of like some latent state consistency term, or not kind of, it is. And the good thing is this bound holds for any encoder, any latent space model, and any policy. So this is kind of like the end of the theoretical part of the paper. And this is like their bound. And then the rest of the paper kind of looks at the practicalities of how can you use this to learn the different parts of the model. And it requires lots of function approximation and I don't want to call them hacks, but like ways around not being able to compute certain things. So this is the algorithm, and they implement their algorithm with deep deterministic policy gradients, but they state that you can use it with any RL algorithm. So, you know, at the start, you initialize your encoder, your model, and your policy. So we've seen these before. And they also now say that you need to initialize some classifier. We'll talk about this later. And also some parameterized reward function and Q function. Now, what these are saying is essentially we need to learn our reward function from the latent space, because currently we have it from the state space, and similarly for the Q function. Okay, so that I think equations 3 to 5 here, lines 3 to 5, are essentially just using the policy in the environment, collecting some data and putting it into our replay buffer. And then at the end of line 5, we sample the sampler K length k sequence from the replay buffer, so a length k trajectory. And they then use this to try and learn the dynamics model using the bound. And yeah, we'll talk about this later, but essentially they start by learning the dynamics model and the encoder. So that's shown here. So they don't learn the policy. The policy is learned in like a second phase. So once they've learned the dynamics model and the encoder, they then compute the lower bound using on-policy actions. So this is nice, because kind of what they could do now is you take some state, you use your encoder to map your latent space, then any policy can be used to, can be simulated in the latent space, which allows us to do these on-policy updates. So that's what's happening in 8 and 9. And then in 10, we update the other parts of our model, the classifier, Q function, and reward. And we'll talk a bit more about those later. So this is the objective for learning the dynamics model. So this is essentially our lower bound, and this is say that input is this k length trajectory that we sample from the replay buffer. And all that's happening here, this expectation is saying we're going to map our state to the latent space using our encoder. Then we're going to roll out the trajectory in the latent space dynamics using the observed actions. So now we have this like joint distribution over the latent states, over the trajectory. Then we have our learn Q function and our learn reward. And these are nice because these are acting from the latent state. And then we have this KL term. And as I said before, this is like a latent space consistency term. So this is trying to make the output of the encoder match the output from the dynamics. So if you imagine now we have each high dimensional image we have, and we map them to latent space, and we're trying to make sure that they match with the ones from the transition dynamics being simulated.
Hey, excuse me, how is the latent reward defined? Because at the beginning it was like an observation space reward. So how did do you have an example later on? Like, what does that actually look like if you don't decode anything at all?
Yeah, so they're essentially just trying to make like given like the latent. So you have an image input, you use your encoder to map it to the latent space. Then you predict with this reward function, and you want the output of that to match the reward function from the state space. And I can't remember what objective they use, but it's just like maybe just like the mean squared error or something. Yeah, so like so they're able to estimate the Q or learn the Q functions and the reward function using transition from the real environment. But essentially, the idea is that they like use their encoder, right? But maybe we can talk more about this at the end if it's still not clear. So yeah, this is kind of the latent space dynamics learning phase. Is there any more questions now before we look at the policy learning?
So what are the parameters in this? Like this, you create some kind of computational graph here, right? Which you need to backpropagate. So what are the parameters here?
So in this part, we're learning the encoder parameters, and we're learning the latent space dynamics models parameters.
Okay.
And then everything else is fixed.
Okay.
But like in this paper, there's quite a lot of things that there's lots of moving parts, right? So like lots of tricks they've done to stabilize the learning. So for example, like they had to add a target encoder network to using the KL to help stabilize that. But yeah, this first phase is like learn the encoder, so the representation and the dynamics model. And then in the second phase, they say, now we've got the representation and the dynamics, let's learn the policy in an on-policy fashion. So this policy learning phase is a planning phase. So I'm just showing now the original objectives so we can do some comparison. So the idea is that this original objective, it requires the states at all time steps. So if we look at the encoder term, we need to map from the high dimensional observation space to the latent state at each time step. And if the idea is what we kind of want to do is we want to have this, they want to have this initial state, map it to the latent space, and enroll it with some policy. But when they do that, they don't have a decoder, so they can't ever know what these states are. And what they do here is they introduce this classifier, and this is the C theta. And this is just trying to differentiate between the predictions over ZT+1 from the encoder and the dynamics model. And they cite some prior work which does a similar thing. But the basic idea is this intrinsic term in the objective, they can replace it by just putting this term here. So the output the classifier over 1 minus classifier. And the beauty is now that all they need to do is take the latent state, map it to take the high dimensional state, map it to the latent space, and then they can enroll a trajectory using any policy. And then you can do on policy updates. So that was kind of everything I was going to talk about the method. There's obviously more to it, like how do they learn the classifier and the reward Q function. But maybe we can chat about that at the end if people want to. Well, I'll stop now. Is there anything that wasn't clear that people would like me to go a bit deeper into? Did anyone understand what I was talking about? I'm going to take the silences.
How do we train the Q function?
Yeah, so this is shown in so here equation 9 I think shows how they learn the Q function. So they're able to do it in the like with observations from the real environment, which is like the nice part. So they use their encoder to map the states to the latent space, and then kind of use that. And again, they have they use a target network again.
Mm-hmm. Okay.
Okay. So in the results, so which is table 1, shows that the policy return after a fixed number of steps in the environment. And here their methods, ALM, gets the best performance in 4 out of the 5 tasks. And so they compare it to soft critic, stochastic value gradient. And they say, so I don't know that paper too well, but that paper is like a very similar setup, except that each part has different objectives, whereas they use like one objective to do it all. There's a few architectural changes, but that was like the reason they used it as a baseline. And they also compare to some other model-free methods, like soft critic and TD3. and another model-based SLBO. So yeah, I think that this part of the paper was trying to show that using the one objective, optimizing everything with one objective, improved performance. So they then tried to compare against ensemble methods. So in model-based RL, well, actually not just model-based RL, like using ensembles of neural networks has just been working really well for sample efficiency. So they compared to model-based policy optimization in blue, and also randomized ensembled double Q-learning in the green, which is actually a model-free method, but they use ensembles of Q networks, and interestingly get state-of-the-art sample efficiency without learning a dynamics model. But what we're looking for here is in the left three plots, we're looking at the average returns versus the number of steps in the environment. So for good sample efficiency, these curves should go up and start to converge quicker. So we see for soft act to critic, which is the model free, this takes quite a long time, but it's increasing really slowly because there's poor sample efficiency. In contrast, all the other methods seem to, well, MBPO is failing on a couple of these environments, but generally they're kind of all have quite good sample efficiency. But the main result they were trying to show is on the far right plot, which is showing the wall clock time. And their method in the red has way faster because there's no ensembles. So I think they sort of argue with this figure that they get similar sample efficiency to like MBPO and red Q, but the wall clock time is 10 times faster for MBPO and 6 times faster than red Q because there's no ensembles. They then analyze the Q values. So I think I understand this figure. I was a little confused. But the left plot is showing the bias in the Q network. So I think so positive values mean that they're overestimating the Q value. And I think they wanted it to be negative, but because they use function approximation in their practical method, they can't always guarantee it. But it kind of shows it's positive a bit at the start and then it becomes negative. And that's a good thing. The right-hand plot then looks at the standard deviation of the bias. And this is essentially saying that when it's low, and it's low for like most of the environment steps, the actions which are maximizing the lower bound are actions which are maximizing the sum of returns, the Q value. So which kind of alludes to their objective being really good for getting actions, not good actions. They do some ablation experiments. So here the top row is in the half cheetah environment and the bottom row is in the ant environment. And each column is like a different experiment. But in the left-hand column, they essentially remove different part from their objective. So again, we're looking at the average returns against the environment steps. So red is just their method with a horizon at k equals 3. And that does pretty well. If they remove the KL divergence term, so that was like the latent-space consistency, then the method just doesn't work, which kind of makes sense because everything's in the latent space. If you don't have that, it won't work. They tried to remove the classifier C, and they show that this leads to unstable training. So we can see this happening in the ant environment. They then also removed the value function, and it appears to have no impact, which is quite interesting. Would have thought that would have been important. In the middle column, they look at the sequence length, so like what value you choose for K. So here the green ALM1 is using K equals 1, and it does pretty well in both environments. When we increase it to 3 in the red, similarly, the performance gets, if anything, the performance gets a little bit better. And then in the red, when they put k equals 5, so it seems to get better in half theta, but in the ANSIT, to me, like, this is pretty bad. And in the paper, they say that their method is robust to the value of k. And I would say that their figures actually say the opposite. So I don't know if they've put the wrong results in or if they've spoken about it wrong. But I'm a little confused about this. If anyone disagrees and they think I've misunderstood this, then please shout. And then the right-hand column. So I'm trying to get my head around this result. Like, I'm not fully sure how they've implemented this, which has made it quite hard to understand. So I think they train their model using a k equals 3. And then I think what they say is they have this encoder, which is like some latent state representation, and they have their Q function and reward function in this latent space. And I think they then say, let's throw away the dynamics model and do model-free reinforcement learning using their like latent representation. So that's what the red line is. And they show that they still get really good sample efficiency using model-free in their representation relative to the other methods, which are all model-free methods. I think this is really interesting because I think it's kind of saying that it's this latent representation that they've learned with the encoder and then learning the value function in this latent space has given them the sample efficiency, perhaps more so than the dynamics model. But I think in order to have learned any of them, I think they needed the dynamics model. Yeah, I need to think about this result a bit more, but nevertheless, like, quite interesting. They've been able to throw away the model and still get really good sample efficiency. Finally, they look at they try to analyze their learned representations. So here they're essentially just looking at one of the dimensions of the latent state over time steps. So here the red is a prediction from their model, and then the dashed line is a ground truth. So the ground truth is essentially they've taken the environment observations and they've mapped them through their encoder, and then they've seen if they match. And they match pretty well, up to 20 steps. And then they show if you remove the KL term, so the latent state consistency, it doesn't match, which is again to be expected. And then the right plot kind of just is a different view of the same result, really. It shows a normalized model error over time or trajectory steps with and without the KL. So the error kind of grows, but not too much relatively. If you don't have the KL term, then it grows quite a lot more. Okay, so to summarize, their one objective for learning the representation, the latent space dynamics, and the policy. And they're able to get similar sample efficiency to the state of the art for good sample efficiency. So MBPO, which is a model-based algorithm, and RedQ, which is model-free. But because they don't use ensembles, it's 6 times faster and 10 times faster for MBPO. Okay, thank you for listening. I did have more slides, but I thought it'd be nicer to sort of open up the floor for questions, and we can talk a bit more in depth.
Yeah, thank you for the presentation, Aidan. So I guess we have about 8 minutes for the discussion. So yeah.
Aidan, so can you comment? So if we don't have the model, what would be the algorithm? Like what kind of parts do we drop and what do we actually learn?
Yeah, in wait, where is it? The right hand plots
here. Yes.
Yeah, so this has been the hardest part to get my head around, because there's one line which kind of says everything. What did they say? So they say we perform a third ablation experiment, which uses the TD3 actor loss for training the policy. The ablation investigates whether the representations learned by ALM are beneficial for model 3. And that's kind of all they say. So I think they need the model in order to learn these representations. But the idea is that they, in the policy learning phase, where they normally use a model to simulate trajectories, they essentially take K to 0, like the rollout length to 0, and treat it like model 3, I think. But they use the learn Q function in the latent space to do the bootstrapping. So we have this so the objective on the bottom line is what's normally used for policy learning. So I think here, I guess K in the dynamics model is much lower, or is 0. So you map a state to the latent space, and the expectation is over just this single time step, and then the rest you then, or I guess you could then. I mean, if you're going to do TD3, then you have your free states, you map them all to the latent space, you calculate the reward in the latent space, and then you bootstrap with the Q function in the latent space. And then you're just doing TD3 in the latent space using the encoder. Does that make sense?
But when you train the encoder, you still use the loss that you showed on one of these previous slides, right?
This is what I think. Yeah, I think because I don't see how else they could learn it. This is what I'm not too sure about. It's not spoken about. But yeah, I think they still need to use the dynamics in order to learn this, because they need this latent space consistency term to learn the encoder, and that requires the dynamics.
Mm-hmm. And from the results, it doesn't seem that the model actually helps much, right? If you compare the right-hand side plots with the left-hand side plots in the, yeah.
Wait, is this one?
Yeah.
Well, I mean, if you look at the scale on the x-axis, it's different, and for the half cheater experiments. So it's it has helped a little bit in terms of sample efficiency.
Mm-hmm.
But yeah, I was thinking about this. If so the idea is they have this nice learned representation. So one of the issues with model-based RL is that the dynamics model you learned is kind of conditioned on the reward function, right? Because you're conditioned on the state transitions with the policy using that reward function. So actually, it's not that easy to plug in a new reward function and solve a different task. And I'm wondering if their argument is, you have this latent representation. So if you have a new reward function, no, actually that won't work. Ignore me. I was going to say they could plug it in, but then they can't because they've learned the reward function. So yeah, I don't know.
So my understanding is that the encoder learns representations that are good for predicting the value function. And then you regularize it with this consistency loss. like this is on the high level, the idea.
Yeah. Yeah, essentially. And it should be kind of like trying to this objective will be high when you remain in regions of dynamics which you're certain about. So it will like find policies which stay in regions that it's observed. But I mean, one thing that I did think here is, how do they encode notions of exploration? So I think they just add loads of noise to the action, I think, to get exploration. And so like this expectation over the latent space dynamics, like this doesn't really represent any epistemic uncertainty. This is like, this is just like, I mean, this would just capture like stochasticity, right, in the latent space. So yeah, I was just thinking, would there be interesting ways to extend this by kind of trying to capture the epistemic uncertainty in these different parts, and then use that for exploration?
Yeah, if you look at the evaluations, they just evaluate on very environments with like rewards at every time step. So they like just ignore the whole exploration problem here.
Yeah, completely.
Another thing I'm a bit curious about is this learning these representations. So as I said, they only evaluate this method on state or these state-based tasks like ant and half cheetah. So what if they apply this method to image-based tasks? Is this latent space consistency loss really enough?
Yeah, I did find it interesting when sort of getting to the line where they said they didn't do image-based stuff, because it kind of seemed like one of the points of a method like this might be for image-based environments. But I'm fairly certain, I mean, is he in this meeting? Like, I think a similar objective has been used in the TD-MPC paper. And I think they were using image-based inputs. So I think this kind of KL consistency term does work for image-based inputs. But yeah, they haven't done the experiment, so who knows? But yeah, there's lots of moving parts, which I think like they talk about being like their big limitation. Lots of moving parts, and then lots of like target networks trying to stabilize the learning in different areas. And then there was like some things that they had to do to try and get this to work. So they like, if you look at here, well, if you go back to this objective, the actual objective here has this extrinsic term here, so then the log of the reward. And I think they actually emit that during training, which is, yeah, like apparently including that decreases the performance of the algorithm. And similarly, they had to like scale the KL divergence term here in order to get it to work properly. But what I did like in the paper is, they told us all these things that they've done, and then they, in the back in the appendix, they have a big list of all the experiments that they tried to do, which just failed, which I thought was quite a nice thing to see in the paper.
Hey, Aidan, thanks a lot for the talk. I was a little bit confused with the lower bound bit, where they kind of derive this like actual theoretical lower bound, and then the practical algorithm, it kind of uses a different formulation, or like kind of they do some different things to lower bound. So is it still a lower bound in that sense, or is it like inspired by the lower bound?
Yeah, I think they're like with all the function approximation, I mean, like, it's like not really, is it? Because like they don't really have access to like the true reward or the true Q function. No, they learn them. So there's like this gap between the theory and practice because of all the function approximation. Is that what you were talking about, the function approximation, or were you talking about the
yeah, it's like lots. Yeah, there's the function approximation, then there's these kind of, I don't know, the KL thing that you mentioned. I don't know if that actually comes up in the bound. And then they also have this section where they just say, oh yeah, we don't take the log, we do something else. So I just thought, yeah, now I'm just like, maybe it's
yeah.
yeah.
I do agree. It's super weird, isn't it? How, like, I don't know, it's like nice, elegant bound, but then to make it work, they've had to throw different things away. I mean, I think that the KL is there, right? Because this trajectory is like an expectation over like M. So this is like negative M log M over E, which is a KL.
Yeah, actually, yeah, you're right there.
Yeah. But yeah, I think like this is one of the things that they say is like, this is kind of like an initial attempt to put all of this into a bound. And it'd be interesting to do some more work looking at the sort of gap between practice and the sort of theory, especially because the amount of moving parts in this method.
Okay, so I guess there are no more questions. Yeah, so thank you all, and again, thank you, Aidan, for the interesting presentation. And I hope to see you again in the next session of the reading club. And have a nice weekend. Bye bye.
Thank you.
See you, everyone.